It's okay? Okay, yeah. So anyway, yeah. So my name is Simon Fellin. I work as a lead data engineer at Seven Bridges. And Seven Bridges is a company that do software for optimizing supply chains for companies. So anything from making sure that you're not invoiced more than you should, gathering all insight from all different carriers and providers where you're shipping things all the way up to simulating what is the fastest route from UK to China, etc. So in this talk, I'm going to show the transition that we've done from when I started Seven Bridges, what was in place, all the use cases, and what led us to move towards the Lakehouse architecture. So I'm going to go through that now. So I like to draw. It's nothing fancy. So the very main baseline, obviously this is heavily simplified. So you can imagine there's the platform. The platform has some traditional backend with some relational databases. There can be, or there is, some API sources, such as rates, what does it cost to ship something. And then you have other sources as well, such as, ad hoc data sets from clients. They can come over email or, anything you can imagine. So this is like the baseline, of our data sources, or, in a very kind of simplified way. So what was happening is, in the platform, we were doing some basic SQL cron jobs that would run, logic for various reports, etc. And this is built in such a way that at the time there was a lot of backend engineers, there were business analysts, but not necessarily any data engineer. So you can imagine, the struggle with that. But it was working, and it was doing its job. And then the question comes up: how do we integrate some of these other sources that we have to these cron jobs? There's a couple of applications in the backend that will try to consolidate this. And then on top of all of this, you have multiple read and writes from all over the place, users back and forth, internally, externally to the platform. And to just visualize this a little bit better, you can imagine, like I said, you had some business intelligence. It would go on the read replica, build some dashboards, internal users are happy. And then you have, for clients, they go to the front end communicates with API with the back end, that in some cases builds dashboards straight off the bat, in other cases through iframes, and this also goes on the same business intelligence tool. And this goes round and round, and you can imagine all this going on at the same time. And this was working, and this works given the skill set you have at the time. To complicate things even more, there's also data science use cases. So they would, read data from these read replicas. They would do their thing, load the data somewhere else, and pretty much it. And you kind of end up in a situation, right, where we got data warehouse use cases for reports. We got tons of unstructured data from all these various sources, and we got data science loads that we want to have insights too, and how do we make that visible in the platform? So many read and writes, system can't really keep up. The guys at the time, they did their best, improve the databases, do the traditional indexing, etc., etc. You get to a point where that, you hit your limit. So someone says, let's bump the resources, and you kind of know what happens. Like things get to a choking point, and I'm not necessarily saying that this happened, but there's moments where if we do this is not really going to work if 5-6 more clients come on board. So from that background, essentially, what I did, so I joined Seven Bridges. I kind of went through all these use cases, and I had this idea around data products. So I know maybe some of you here are hardcore data mesh people. I am not. I'm inspired by it, however. So I've kind of taken my own take on it. So from our perspective, more or less there's 3 big steps. So we have different squads. They do various different things in the platform. And at some point you want to do initially some kind of ideation, R&D. You want to have some kind of validation and confirmation stage, and then ultimately you want to have something like a final product that's ready to be deployed, and that becomes part of the platform, which end users can use. So this is what I kind of introduced, that we should try to achieve, which then makes it easier to design the platform itself, rather than just trying to jump on every individual problem. And, everyone who's worked with data know that this can be quite, tiresome and etc. So, okay, what do we need in place to achieve this? So the first couple of things you can do, right, is, okay, what about traditional data warehousing? Yes, we have some structured data, some traditional ETLs, imagine any framework you want, it doesn't really matter. You have some kind of storage and compute in some traditional data warehouse, and you now have all of a sudden excellent way of doing very heavy reads, reading aggregations, getting your core business value out, like traditional reports, etc. So this really works, but it doesn't really cut it for 7bridges use cases. This is just mainly for reporting. So okay, what about if there's some more like data sources that are not from relational databases, so more event-driven? Okay, maybe we can then consolidate with some, traditional data lake in parallel to the data warehouse. Okay, you have some more of a extract load process, you load them into some raw object storage. You then have data science and various other data apps that works on this, and that works as well. And however, you kind of end up in a situation now, but how do I combine all of these things together? Because ultimately these two approaches, they work, but it's not really what we want. So, I created data silos, so, how do I solve it? Well, what about a Lakehouse architecture? So, obviously simplified, but so what we do is, okay, we really want to separate compute and storage from each other completely. And this is because we don't want to force other engineers other than data engineers, to work with very specific tools. Like we want them to be able to build, like for example, data scientists, they love Dask. On the data engineering side, we really like Spark for many cases. And then we have Delta RS, for example, open source Delta in Rust, Python apps, great. And then you have Trino, which is this kind of magic thing that can just kind of glue everything together on top of this. So what if we use Starburst as kind of the metadata governance layer on top of all of this? So just to give some background, before we went with Starburst, we deployed Trino ourselves, we did that whole journey, we were validating different ways. I'm a big fan of Delta, the open source project, so I wanted to use that, but I didn't necessarily want to be locked in. I wanted something that we can use, scale with, and do stuff, as things evolve over time. Okay, so that looks very interesting, but what about, data observability and metrics? So we're pretty, bare bone. We have tons of stuff in place where we do this, traditional Prometheus, Grafana. We run everything in Kubernetes, and we host all our tools ourselves, including Spark, dbt, whatever you name it. And we need to consolidate all these things due to the flexibility. So the great thing with Starburst is they have also metrics around usage, who's using what tables, who is, what's taken the longest query time, what fails out. So we can combine all these, have it in one place. And again, heavily simplified. Okay, so I'm going to try to break down now how this data flows. Like the stuff I showed you in the beginning, how does this actually look in practice? Kinda. And just to give you a few examples, okay, we have some API endpoints, for example, rates. We have some structured data, that could be bookings, shipment, invoices, whatever, that, is more suitable for that kind of operations. We have CRM, Salesforce, and I took rate cards here as an example. So rate cards is more or less information about shipments, transit zones, what does it cost explicitly from different places, airport costs, etc., etc. So this is one of the products we built outside of, traditional backend with a Postgres, etc., where we work directly with the Lakehouse. And I will show some use cases around this later. And for our bare bone, we use Airbyte currently. We host it ourselves. We run it in Kubernetes. We use it for mainly Postgres and Salesforce. And we move this into a raw state. This is very traditional kind of, I wouldn't say ETL because we actually don't do many transformations with Spark in this case. So what we do here is we just move the data. We do this at various speeds. And we do stuff like the data I've just synced, is it still available in the platform or not? So we need to do a lot of soft delete checks, etc. But this is like very basic kind of data engineering work. Okay, so what about stuff that doesn't work in Airbyte? And also, just to clarify, the reason why we use Airbyte is we're a very small team, so we're only 3 people who built this core platform. So Airbyte is a great tool to like speed up things. Anyway, what can we do when we can't use that? Well, so we have internally built a Delta client, which works in tandem with the open source Delta RS and Trino, and we kind of flake these two between each other. You can load data in memory, write it to a Delta table. It's immediately available in Galaxy, Trino, but it's also available for other, like Spark or whatever that can connect with Delta. So this is more kind of event-based. So to give you an example with the rate cards, there's like a UI, someone goes up, they upload a rate card, there's an application that runs continuously, picks it up, writes it immediately to a bronze table, and that's it kind of. And when you look at this, you then ask yourself, okay, so how do we facilitate the basic reporting, essentially the data warehouse use cases? And also, we need to use something that not just data engineers can use. We need something that, to facilitate this data product idea, that even a backend engineer or a business analyst, from whatever route they come from, that they can go in and build their data sets. So we use dbt for this, on top of Trino. Very traditional, kind of, batch flow, picks up the data. We have all the automation around dbt, best practices, linters, etc., to kind of educate the users, continuous tests, etc. And this then immediately becomes available through Trino to Starburst. We build the dashboards. And to give you an example, here, this is kind of basic flow, right? But in the old system, there were several reports that when they were computed, they could take up to 40 minutes, whereas now it runs, it computes in under a minute. So, it does the job, and it does it very well. Okay, so what about maybe more, more in-depth stuff, like more core data engineering type of work? It says stream here. I'm going to be careful and not say stream, so maybe more event, because I will get to also why in a bit. But we use very, very heavily a change data feed, which is the kind of native feature of Delta. So in the rate card example, we have a change data feed, Delta bronze table. We have various structured Spark streaming CDF jobs that will pick this up, push it through the system, do all the good stuff that you expect with great expectations and whatnot. And again, this now all of a sudden combine these two batch and more event-driven approaches into the same storage layer, but they run on completely different computes. So now we kind of achieved what we wanted to achieve. Okay, so you might ask now, looking at this, why are you not using like log-based CDC, like from the Postgres databases? And this is this is something I would love to use. However, we're a startup. A lot of the databases have been set up manually in the past. We're working very hard to migrate them into infrastructure as code. It can be a bit dangerous. Just turn things on, see what happens. So while designing all of this, you need to make sure you're keeping up to date with the best practices and standards. But then you also have limitations. So we're also looking into, for example, removing Postgres altogether in some cases, like the rate cards, where it just goes straight into the system, whereas then you don't need it, right? But this is kind of a natural question looking at that diagram. Okay, so what about data science use cases then? Well, for data science, we use Dask heavily. Again, they use both native Dask. They also use the client. So they might do compute in Dask on Delta on the tables, and then they will use the client to register them to Trino. So immediately other teams who want to consume this can access it, for example, in another Python app. So all of a sudden you have this really cool environment where people are contributing, they're using their own tools, and we're looking them all together and making it usable. Yeah, so this together is, kind of our Lakehouse architecture. And obviously this is evolving, it's growing, we're trying to improve things, we're scaling up, educating other team members, other squad members that are not necessarily data engineers, etc., etc. And another interesting thing is, so anyone who's worked with Delta, especially in this kind of environment, they know that, okay, what about concurrent writes? So, how do we handle this? Well, we have kind of figured out a pretty interesting way where, we have a scenario where we have the client, we have multiple Trino clusters, we might have a Dask cluster, and then we have a separate kind of lock mechanism that wraps all this together and make sure that we can basically we can get that isolation. So if someone writes from Dask, it won't collide with like a Trino write or vice versa. And just to try to explain this graph, so what happens is you install the client. In the first scenario, you make a request to any of these Trino clusters. The Trino clusters, the request won't go to the cluster until we have verified the lock. So in the client, it will try to acquire a lock for that table that you're trying to write to. If it's free, it will send the request. Trino will do its thing. Once it's done, we release it. And then at the same time, like I said, like some of these Dask workers might be trying to write to the same table. All of a sudden, we kind of solve this problem. Obviously, this is not, at the moment, not working in tandem with Spark that we're using. And it's something we're working on to improve. But it's quite interesting. I realize I'm very ahead of time. So I thought it would take longer, actually. So I kind of sped it through very quickly. So there is time for questions. If anyone wants to ask something about this. Maybe not. In that case, I guess that's it. And I will be in the booth if anyone changes their mind. So, yeah.